Okay. So it's a pleasure to introduce David Wilson from Microsoft, who will talk about Oded's work on Boolean functions.
Thank you. Okay, I'm still going to be talking about how these Boolean functions tie into random turn games and percolation. So remember at one point, Oded declared that he didn't intend to work on Boolean functions anymore, but then we had Ryan O'Donnell as a postdoc, and Itai was visiting, and Mike Sachs was visiting, and somehow this was too much to resist continuing work on Boolean functions. So so we're going to, well, there are two conventions. So we're going to have the functions map -1, 1 to the n, to -1 and 1. And so one particular question that we looked at, and this was with Itai and Oded, was the following. So if you have a function and you have a way of evaluating it by a decision tree, so what the tree does is it looks at bits one at a time, makes a decision as to what bit to look at next, and then read the next bit, and at some point it stops reading bits and outputs the value of the function. So delta I is the probability that the ith bit is read. Okay, and we say that delta of t is the maximum over I of delta it. And delta of the function is the minimum over decision trees of the maximum probability that a bit is read. Okay, so so how small can delta be? All right, so just to give some example Boolean functions. Okay, so if the function is always 1, then delta is 0. Okay, and so to rule out this degenerate case, we require the function to be balanced. And what a balanced function is the expected value of the function on a random input should be 0. So half the time it's 1, and half the time it's -1. Okay, so there's the dictator function, which always returns the value of the first bit. And for that, delta is 1, because you always have to look at that bit. Majority okay, so this is order 1. You have to look at most of the bits in order to figure out what the majority is. And this is in contrast to the related concept of the influence of a bit on the random function. So what the influence is the probability that f of x is not equal to f of x with the ith bit flipped. Okay, so this is the influence of the ith bit. Okay, and so for here, for majority, the influence is pretty small. It's order 1 over root n. Okay, so another classic example Boolean function, which is due to binor and lineal, is the tribes function. For this, you have 2 to the m blocks of m bits, and if any of these blocks are all 0, the function is 0, or I should say -1. Okay, so for tribes, the influence is log n over n, which is small, but delta is still pretty big because you have to look at most of the tribes in order to verify that the function isn't -1. But for any given tribe, you only have to look at order 1 bits typically, and so it's order 1 over log n. Okay, so we constructed some example for which delta was 1 over n to the half times square root of log n. And I don't really want to describe the example in great detail, but there's an easy lower bound of 1 over root n for any function, and that's just because if each bit is read with probability at most 1 over root n, you're looking at fewer than root n bits, and if you have an independent input and an independent run of the algorithm, there's a good chance that the 2 runs will look at different bits, different collections of bits, and furthermore that they'll have different answers, and then you can just sort of combine the 2 inputs, and the algorithm would, you can't decide what to output for that case. So, all right, so that's the lower bound here. And for this example, the influence is also 1 over root n times root log n. Okay, so then we also looked at monotone functions. And for that, there's some construction that gives 1 over the cube root of n. And turns out the influence is 1 over n to the 2/3 log n. So this is based on a branching process, but I won't say too much about the actual function. So what I want to talk about is this. So there's a matching lower bound, 1 over n to the 1/3, which holds for any Boolean function. And any monotone Boolean function, yes, thanks. That was proved by Oded, and I'll say a few words about how this proof goes. Okay, so this is the Fourier coefficient corresponding to a set S. This is the expected value of f of x times the product of I and S of x sub I. And for monotone functions, the influence of the ith bit is just the Fourier coefficient on the set containing I. Okay, so there's a bound due to Servideo and O'Donnell and Servideo, which is that if you were to sum up these Fourier coefficients. This is at most the square root of the expected number of bits read by any algorithm that evaluates the function. This is for any function f. Okay, and so this is a down-answer video. Okay, and basically the way the proof works is that this sum can be expressed as an inner product and so this is by Cauchy-Schwarz, and most let me first rewrite this slightly.
Just on the right. Just on the right. The left doesn't need it. And remove the left expectation.
All right. Okay, so this is sum over I, f of x squared, sum over I, x of I, 1 if the ith bit is read. Okay, so f is plus or minus 1 valued. All right, so this evaluates to 1. And here, if you expand this, so you get a term if both bit I and bit j are read. And if I and j are different, in expectation this is going to be 0. And so you only get the diagonal terms here. And okay, so this is x of I, which is always going to be 1. And so you end up getting the expected number of bits read. And okay, so this also follows from an inequality due to Schramm and Steiff, which is that if you sum over sets of size k, this is at most delta k times L2 norm of f squared, which for Boolean functions is always going to be 1. So here you would take k equal to 1 and do some manipulations and get a similar inequality. Okay, so there's another inequality which is due to O'Donnell, Sachs, Schramm, and Servideo, which we need. And that's that the variance of a function, Boolean function, is at most the sum over the input bits I, delta I for any decision tree, times the influence of the ith bit. Okay, so for balanced functions, the variance is going to be 1. This is upper bounded by most delta. Okay, and then we get the sum of the influences. And for monotone functions, the influence is just this Fourier coefficient, which then by O'Donnell Servideo is at most this. And so that's expected number of bits read. The number of bits read is at most delta times n. And in the end, this gives that delta has to be at least n to the minus 1/3. Okay. All right, so I'll say a few words about how the O'Donnell, Sachs, Servideo, Schramm inequality is derived. So what they do is they say that if you look at, say, x and y are independent bit patterns, you look at the expected difference between f of x and f of y. And if the decision tree is going to look at bits I1, I2, and so on, up to IS in that order, we're going to define e sub 0 to equal to y except, or the notation that they use is x at I1 up to IS times y. So what this means is that it's equal to y except at these bit positions where it's equal to x. E1 is the same thing, except starting at I2. And then E sub s is equal to y. Okay, and so by the triangle inequality, this is at most the absolute difference between f at E0 minus f at E1 Okay, and so if you take a generic term in there, f at u sub t minus f minus 1, f at u sub t, this is the sum over I of, well, the same thing, times 1 if the I sub tth bit read is equal to I. Okay, so if you condition on the bits that you've read up to time t minus 1, then what you have in u sub t minus 1, well, that was just equal to y, except at these bits that you haven't read yet, where it's equal to x. And so this is conditionally just a random input. And if you compare it with u sub t, that's just the same random input, except re-randomized at the bit I sub t. And okay, so if you subtract these, then conditional on what you've read so far, the expected value of this is just the influence of the ith bit on f times the probability that you read bit I at time t. Okay, and so then if you sum over all i's and sum over all t's, this gives the right-hand side over here. And the expected absolute difference here is basically the variance of the function. So that's how they got their bound. Okay. All right, so basically the O'Donnell Sachs-Schramm video band says that the products of these two has to be at least 1 over n, and it's reasonably tight for several of these examples. Okay, so I guess I have a few minutes left, and so I'll tie this into random turn games. And okay, so how about if I start the projector? All right. All right, I apologize for the technical difficulties here. All right, so this is one of Oded's favorite Boolean functions here. If we percolate, that is. Okay, so we're going to tie this into random turn games. So, okay, this is the game of hex, where at each turn a coin is flipped to decide which player moves next. And in this case, the computer is playing against itself. And so this is from work with Yuval Perez, Scott Sheffield, and Oded. And so one thing that we show is that the probability that one of the players wins is equal to the probability that you'd have a crossing in random percolation. And you can show this by induction. So
Not just on this board, but
on any board, yes, that's right. Okay, so it's true if there are no moves left or if there's one move left. And okay, so suppose that you've shown it if there are almost k moves left, then if there are k plus 1 moves left, you can verify that the best move for black is the site that's most likely to be pivotal, and that's also the best move for white. And all right, so anyway, the probability that black wins is the probability of a black crossing in this game. Okay, so all right, so from work of Smirnov and Werner.
You say that you toss a coin and decide who moves it each step.
Yes, I believe I said that.
Yeah, you didn't say what the game was and what you have to do to win.
All right, so white wants to connect the white sides, black wants to connect the black sides, and they toss a coin to decide who moves next, and they can't move tiles. Once they're placed, they're placed.
What was the last thing you said?
You can't move tiles. Once you lay them down, then there they stay. Okay, so this can be viewed as a decision tree algorithm. So the players play optimally, decide where to move, and you can, instead of having the coin toss decide who move next, they agree on their common best move, and the coin toss is the random bit. And from Smirnov and Werner, we know that the influence of the bits near the middle is going to be, for an L by L board, L to the minus 5/4. And then from the O'Donnell-Cervidio bound, okay, first of all, this is a monotone function. If we do summation over all sites, this is going to be L squared L to the minus 5/4. Right, which we then square. And so this is, all right, so this is at least that. At least L to the 3/2 plus little o of 1. So this says that if you were to evaluate this percolation crossing function, no matter which strategy you use, it's always going to take at least L to the 3/2 coins to uncover and decide what the function is. And for random turn hex, experimentally, the exponent seems to be around between 1.5 and 1.6. And I think I'm about out of time, so I'll stop here.
Questions or comments?
So about random turn, so you don't expect this to be optimal, right? Or do you have any guess? It's an optimal strategy for the players, but it's not optimal in terms of.
We don't know any better algorithm. Maybe it's optimal, maybe it isn't. We don't have an opinion. Yes?
So I have two short comments. One is that this whole project actually also started from a hike with Wendelin in Rattlesnake Ledge, where he, on the hike suggested that there should be a connection between percolation and hex because they are happening on the same board. And so you should take seriously his suggestions to, play various games because they've worked out. And the other comment is that there's a lower bound of L to the 3/2 for the length of the game that we get from the argument that David told you, but the embarrassing thing is we don't know any upper bound. So Well, the game lasts its most L squared step, but it's about L to the 2, less than L to the 1.6. But show less than L to the 1.99. L to the 2 minus epsilon for the length of the game. We don't know even that.
Okay, I think we'll have a short break. Okay, so it's a pleasure to resume the session with the next talk by Christophe Garban on Oded's work on noise sensitivity.
Okay, so first I would like to thank the organizers for this conference, which enables all of us to remember Oded and his mathematics. I had the chance to work with him during about 2 years, and let me tell you that it was an amazing experience. Maybe I should say quite an amazing experience. So I could experience many things that Van Lin described this morning, like, for example, when we worked with Gábor and Oded, and some strategy completely collapsed, which happened very frequently. Then the next morning, Oded would come with something completely new. So I experienced many of these things. The only thing that changed from 1999 to 2007 was that Sokoban was transformed into football, maybe. So in this talk, I will present one of the many fields in which Oded made great contributions, namely his work on noise sensitivity of Boolean functions. But I will restrict things to the case of percolation. So we will encounter Boolean functions, but applied to the case of percolation. So what we will see is that when you look at critical percolation in the plane, and you're interested in macroscopic properties of this percolation, these macroscopic properties, they are very sensitive to perturbations. If you change just a little bit the picture, your large-scale connectivity properties will be completely damaged. So we will see that this will correspond to the following phenomenon, to the phenomenon that macroscopic events, in some sense, they are of high frequency. So we will see what I mean by this. So just to illustrate this perturbation to this sensitivity to small perturbations, here I have a simulation of a critical Z2 percolation. So at PC equals 1/2. And I've drawn the 3 largest clusters on the left. So the red one is the biggest, and then the blue and the green. And on the right, it's the same configuration, except there are some mistakes. So, or rather, I noised a little bit the left picture. So if you have good eyes, you would see that the 2 discrete configurations are in a way very close. But nevertheless, the macroscopic properties, they're very different.
What's the noise level?
Well, I cheated a little bit because it's not that macroscopic. So here the noise is maybe 0.1 or something like this. So the noise here, it means that for each single edge, you keep the edge with probability 1 minus epsilon as it is, and with probability epsilon, you resample it. So here so one of the motivations that Oded, Itai, and Gil had at the beginning when they looked at these things was to start a route towards proving conformal invariance. So I won't go into this because Stas found a simple route. But another motivation was to study a model called dynamical percolation, which is a model which is the analog of Glauber dynamic, but in the case of percolation. And here I have a movie done by Oded, but I don't know if it looks it's going to work. So this movie done by Oded, you see a percolation on the triangular lattice. So imagine this thing in the whole plane. And each bit evolves according to a Poisson process. So you have your critical percolation, which is evolving in time. And what was expected from the very first paper on dynamical percolation was that even though at each fixed time you see a critical percolation, so almost surely you see only finite clusters, when you run the dynamic, you will have some explosion times where an infinite cluster should appear. So this took several years to be proved, and it was proved by Oded and Jeff, and I'll mention this later. But in order to prove that you have such explosion times, such exceptional times, you need to show that somehow at large scales, the system is moving really fast, so that sometimes it can catch infinite paths. So you need to prove these kind of sensitivity statements that large scales properties, they move really, really fast. There is a fast mixing property for these things. Okay, so these are the motivations to understanding this instability. So in percolation, we are mainly interested in clusters, in connectivity, and things like this. And these large-scale connectivity properties, they are naturally encoded by Boolean functions. So for example, if you take a large rectangle, you may ask if there is a crossing or not from left to right. So this is a Boolean function, and this is the same kind of Boolean function as the one David talked about at the end of his talk. So it's defined very simply like that. It's going to be 1 if there is a crossing and 0 else. And we are going to consider this Boolean function on larger and larger scales. So remind the movie that I showed at the beginning. So omega 0 would be the initial configuration. And if you look at the configuration at a later time t, small time t, then again you have this noised configuration of the initial one. So between omega 0 and omega t, you change a small proportion of hexagons. So we will look at Boolean functions of this big scale percolation configuration, and we will wonder how sensitive they are to this type of noise. So how to quantify that a big connectivity property like the Boolean function we had before, how to quantify that it mixes fast or that it loses its memory very fast? Very simply, we can quantify this with the covariance. So we can look at the covariance of having a crossing at time 0 and having a crossing at time t. And if these covariances, they converge to 0, it means that you lose the information. So a fast decorrelation of macroscopic properties will correspond to these covariances going to 0. So noise sensitivity corresponds to the vanishing of these quantities here. Maybe the second one, you can think of it as you know what the initial configuration is, and you know that a small proportion, roughly t, of bits has changed. What can you guess about the outcome fn of omega t, about the crossing event at time t? If it's noise sensitive, this variance is going to 0, so basically this means that you can't guess anything. So note that defined in such a way, noise sensitivity is not a quantitative statement. And in order to prove that you have explosion times, we will need more quantitative versions of noise sensitivity. And what I mean by this is we will need to know at what speed the large-scale system decorrelates. So we will need to know at which speed these covariances they converge to 0. So the natural setup to look at these things, and I think Itai once told me that initially Oded was not so much convinced about this, but his later contributions proved that finally he was convinced and he was very comfortable with it, is to work on the Fourier side. So I quickly recall harmonic analysis of Boolean function, but David used some of it just before. So we view all Boolean functions in the larger space of the L2 space and the hypercube. endowed with this natural scalar product. And when you do Fourier analysis, you just need to find a natural and convenient orthonormal basis. And here there is a very natural and convenient one, which are the characters of this group. So this orthonormal basis is indexed by the subsets of the bits, S subset of this. And for each of these subsets S, the character corresponding to the subset S is just the product of the value of the bits on this subset S. So this gives you 2 to the n such functions, and it's easy to see that they are orthogonal. And so doing Fourier analysis on the hypercube is just projecting your function on each of these 2 to the n characters. So this gives you Fourier coefficients. And for example, the Fourier coefficient corresponding to the empty set is just projecting to the constant, so this is the average. So we will see that when you take any Boolean function and you look at the sequence of its Fourier coefficients, it will encode interesting properties for us. So why is it helpful in our study of mixing or sensitivity of the Boolean functions? It's just because the covariances are easily expressed in terms of the Fourier coefficients. So if you want to compute the correlation between time 0 and time t, then you write down your observable on you project it on your basis, and then you use the fact that for 2 different characters they are orthogonal, so only the diagonal terms remain, and you end up with this simple formula here. So try to remind this formula for at least the next slide. The covariance is the sum of the Fourier coefficient squared times this e to the minus t times s. So you notice here that if your Boolean function has coefficients of high cardinality, then the covariance is going to be very small. On the other hand, if your Boolean function is supported on low frequencies, then this is going to be stable. Okay, so this agrees with the usual intuition. But what will be important for us when you have a Boolean function will be this, what I think physicists call energy spectrum, which represents the contribution for all k between 1 and n of the level k Fourier coefficient. So if your Boolean function has a distribution which is more on the right, then it's going to be more sensitive than if it's stuck on the left. So just using Parseval, you can see that the total mass of this spectrum, where we don't need to use the empty set, corresponds to the variance of your Boolean function. So now in percolation, what we will need to do, we have these Boolean functions f of n, which corresponds to left-to-right crossing in boxes of scale n. And we'd like to know what is the shape of the energy spectrum of this Boolean function. Is it located near finite frequencies, or does it spread to infinity? How does it look? So we'd like to describe the shape of so recall Fn was this type of Boolean functions. We'd like to describe the shape of their energy spectrum. So, and if we want a quantitative statement on the sensitivity of percolation, we want more. We would like to know at which speed the spectral mass will diverge to infinity. So just as a comparison, I've drawn here the energy spectrum of the majority function. So in this case, you can compute things explicitly. And you can see that in some sense, most of the spectral mass will be localized on finite frequencies. So we expect that in the case of percolation, it should look very differently. So there are basically three very different approaches to try to localize where the spectral mass is. So the first one was done by Oded, Itai, and Gil in '98, and it used techniques brought from analysis. And so I'll mention what their result was later. The second technique was a technique based on randomized algorithm, and this is something which is related to the previous talk a little bit. And the last one was the work we had many attempts and with Gábor and Oded, and finally it worked. So you can, when you look at these approaches which turn out to be very different, you can see that there is a common denominator to these three. And if you don't see, then I can help you. So, okay, so now I just present these results. So the first one, before saying this, from the beginning there were heuristical arguments which say that which speed the spectral mass should diverge at infinity. And it's even more than this. You can prove that a positive fraction of the mass will spread at this speed here, if you know the critical exponent. But what was a little bit embarrassing is that even though you know that a positive fraction diverges really fast, it could still be that you have a positive fraction lying at the bottom part of this distribution. And it turned out to be hard to handle the lower tail of this distribution. So the first result that I mentioned, which uses hypercontractivity, and which uses ideas that came from analysis but also computer sciences at the time, proved that the spectral mass diverges at least logarithmically fast. So stated in terms of Fourier coefficients here, it means that asymptotically you don't have mass on the finite frequencies. So this already proves you a noise sensitivity statement. So the second result with that they did with Jeff went a little bit further and proved that the spectral mass diverges at least polynomially fast. But they proved more. They gave a bound on what is the lower tail of this energy spectrum. And this lower tail control enabled them to prove that there are exceptional times in the dynamical percolation model. And finally, with Oded and Gábor, we could go all the way to the expected n to the 3/4 with a sharp control on the lower tail. So maybe I should insist here that even though on the third approach we can go all the way to n to the 3/4, these two approaches, they have the advantage to be much more general than the one we did a priori. For example, the one that uses hypercontractivity in some sense says that if you take any Boolean function so that each of its variables have very influence on the outcome, then you will have a logarithmic control on its Fourier spectrum. So somehow their methods here are you can apply them to many cases. And as well in the case of the work by Oded and Jeff, if you have a randomized algorithm which computes your function so that it looks at very few bits, then you will also have a very good control on the Fourier spectrum. So maybe the third approach could be applied to other things, but it's not clear yet. So just to say a word on the last approach, and then I will describe in more detail the green one, the one with Jeff. The last approach, it's in the real case, if you would have a function in L2, and you look at its Fourier transform, then the square of this Fourier transform, it defines you a probability measure on the real line. So you can see this as a random variable for each function f, you can see this thing as a random variable on the real line. For a Boolean function, you can do exactly the same, but this time, instead of having a probability distribution on the real line, you will have a probability distribution on the characters. So you will have a probability distribution on the subsets of your bits. And very roughly speaking, the idea of the third approach is to sample uniformly, to sample a frequency according to this measure. So this will be some subsets of, so if your Boolean function is the left to right crossing of before, it will be some random subset. And this random subset was believed to be very close to the pivotal points of percolation, but it turns out that this actually should be different. And the goal was to try to study the properties of this random set and to try to say that in a way, this is close to a random Cantor set a little bit. But the difficulty was that the dependency structure of this random set is a little bit hard to analyze. So I won't describe more the red and the blue approaches, and I will now try to describe more the algorithmic approach that he has done with Jeff. So this is based on randomized algorithms. So what is it? So if you take a Boolean function f from the hypercube into 0, 1, a randomized algorithm is something that computes the function f by examining bits one at a time. So you take a first bit randomly or according to some procedure, and depending on the value of this first bit, you choose a new one, and so on until you discover the output of the function f. And an algorithm for us will be efficient if you manage to compute f using the smallest number of bits. So to quantify this, I use the same thing as what David talked about before, which is the supremum over all the variables of the probability that the variable is used along the algorithm. So this is called the revealment. And for an algorithm A, we will call J the random subset of the bits which is actually used along the algorithm. So, well, David already gave the example of majority. So majority, there is nothing really smart to do. You just need to ask people one at a time, and you'll need at least to ask half of the people, and it's easy to see that with high probability, you'll need to ask many. So the revealment is not going to be very good. So you could take other examples like recursive majority, and here you can, I won't do it, but you can easily find algorithm which will ask very few people. So we're interested in percolation. So what would be a natural randomized algorithm? Well, we've seen it already several times today. So say you want to have the left to right event here by white hexagons. So one idea that is present in all the work of Oded on 2D percolation is to use exploration paths. So here the randomized algorithm, you can ask what is the value of the first hexagon, and depending on it, you continue your exploration path, and so on. So if your exploration path ends up being here, the Boolean function is going to be 0, and else it will be 1. So this is a nice randomized algorithm, but not so nice because it makes the revealment equal to 1. Why? Because here I always ask the value of the first hexagon on the top left. There is an easy way out. You can randomize the departure of the exploration path, and maybe you'll need at most 2 exploration paths to be sure of the result, but eventually, by randomizing the beginning, you can have a nice randomized algorithm computing the left-to-right crossing. So let me just tell you what will be the revealment for such a for such a function. Asymptotically, the bits used by the algorithm, this J set, it will be this SLE6 curve that Van Lin mentioned this morning. So asymptotically, you see that the amount of bits which are used by the algorithm is very small because this curve occupies a very small fraction of the window. And since we know that this is something of dimension 7/4, it easily implies that the revealment is of order n⁻⁻⁴. So there are some boundary issues to play with, but this is standard in percolation. So for left to right crossing on the triangular grid, you can have algorithm with very small revealment. So now how does it, what does it say about the spectrum itself? How does it help us to localize where the spectral mass is? Well, there is I think very nice, and the proof is very short, of this theorem, which was done by Oded and Jeff, and was mentioned by David before. So if you take a Boolean function on the hypercube, and even a real valued function, and if you have a randomized algorithm which computes f of revealment delta, then only this information gives you deep information on the spectrum. For any level k, it will tell you that the level k mass of the Fourier distribution is dominated by k times the revealment times the L2 norm squared of f. So in particular, in our case of the percolation crossings, since we have a very small revealment, then we directly have an information on the lower tail of the Fourier distribution. So in the time remaining, I'd like to explain how to get this result here. So we start with some function like this, and we have this algorithm with revealment delta, and we would like to have a bound on the level k Fourier coefficient. So to do this, we can look at the projection of the function f on the level k characters. So we look at the function f, but only on the level k frequencies. And so the only goal is to estimate what is the L2 norm squared of this function. So what we want to prove is that this is less than k times delta times this. That's the theorem. So how to do this? Well, first notice that the L2 norm squared, this is the same as this. And now we want to use the knowledge of the fact that we have an algorithm and the fact that it has a small revealment and so on. So knowing the information coming from the algorithm. Now the function f is computed by the algorithm, so this is measurable with respect to this algorithm A. So this is going to be this. And by Cauchy-Schwarz, you get that this is less than the norm of f. So now the goal is to try to bound this expectation here. So let me just try to take a simple example to see what's going on. So assume we have 6 bits, so x1, x2, x3, so x5 is x6. And say we have some Boolean function, but we only look at the projection on the level 2 coefficients. And say that once projected, we have some coefficient times x1, x2, plus some coefficient times x1, x4, plus gamma times x5, x6. So basically, we have this frequency here, this frequency here, and this one. And now say that you compute your function f, which is above this function g, right? And say that the randomized algorithm is going to look at these 3 variables. So f is computed, but j is not computed completely because it's. So what is e j of a here? So in that case, if you know what the algorithm here, this conditional expectation is going to be alpha times x1, x2. Here you didn't learn anything. Then you will have beta x1. So let me write it like this. So this term is a constant because you know what it is. The algorithm told you what it is. And then you have a last term, which is gamma x5a, x6 of a. So this is a constant term. This is a level 1 term, and this is a level 2 term. So all of this to say that once you apply the algorithm, you have a kind of collapsing of the frequencies from the size k to the smaller sizes. And the whole game is to get a bond on the collapse on the empty coefficient.
When you say expected value, it's just you mean still the expected value on the right. So you say that all the others go to 0.
Yes. So right. So here it was not the expected value. It was don't know how to write it, but actually, I want to write it like this. So this is the random function which depends on the algorithm and on the set j that you visited. And this is the expectation of this thing, which is the expectation of j knowing a. And here you only keep this term which is constant, and the other one they vanish. So this term is basically the average of this random function when you average over all the other bits. So we can write it like that. Okay, so here when you run the algorithm, you discover some sites, and you have all your frequencies floating around. And when you discover a whole frequency, this goes to the empty coefficients, and this accumulates, and you want to say that if the revealment is small, this is not going to accumulate too much. So now just to bound this thing, so this is the expectation of the squared of the empty Fourier coefficient for this random function here. And we can write it like this. So by Parseval, this is going to be exactly this. So in some sense, it's not so easy to study this collapsing procedure. So Oded and Jeff had this trick to reverse the study. And now, what to do with it? Well, the expectation of this is just the expectation of g squared. And, okay, so we get this. And now we don't really know what to do with the frequencies which are of size other than k. So we just bound. So far we didn't lose anything in our control of the Fourier mass. But here we bound by saying that this is less than g squared minus only on the size k coefficient. And this gives us so E of j squared, this is the sum of this. And we subtract the sum of this thing. So these are also the coefficient of j. This is the same. So now what do we do with it? Well, when you have a frequency somewhere on your set of bits of size k, just 1 minute, then now you send the algorithm. It will reveal sites one at a time. If for this frequency here you reveal one of the sites, then the frequency here will collapse to the size smaller. So for this to be non-zero, you need the algorithm to avoid the frequency here. But now individually each site of this size k set has probability at most delta to be visited. So the probability that the whole thing is visited will be less than k times delta. So this is non-zero only with probability k times delta. So this is going to be less than k times delta, sum over s equals k, like this. And this is g squared. And well, if you plug in the Cauchy-Schwarz estimate that I had before, this gives you the theorem. Okay, so this estimate gave a lower bound on the energy spectrum of percolation, and also for the radial event, and that's what gives, by second moment analysis, the existence of explosion times. Okay, so.
Questions or comments? I think we'll thank Christophe again. And we will start without a break. No? So it's a pleasure to introduce Gábor Pete, who will present a talk on how to prove tightness for the size of strange random sets.
Mm-hmm. Thanks. Okay, so this is Oded, fetching water for our dinner with Christophe and Montrainier. So the water is coming from inside the glacier. So officially the trip was unsuccessful in the sense that we didn't get to the top. We had to turn back from 4,000 meters about. But I really enjoyed it, and it was a great experience for me. So I'm very grateful to Oded for the hike.
I have a question. How
Yes.
do you get them to turn back? How did you get him to turn back? I was never able to do that.
Okay, ask Christophe. But he was okay.
Probably worried about one of them.
Okay, so the photo is not related to the talk, except that the people involved are the same. So it will be a continuation of Christophe's talk in the sense that this strange random set that I'm talking about is based on the Fourier coefficients of critical percolation. But somehow the story is interesting also more generally. So we'll try to explain that. And also, I think whenever we gave a talk on this paper, we never managed to get to this last point. So I tried to remedy this. Okay, so Christophe gave the introduction, what the Fourier coefficients have to do with noise sensitivity, but I recall very briefly. So, okay, this is difficult. Okay, anyway, so when you have a finite set V and you have all the possible plus-minus configurations, say with simplicity with uniform measures, so say all black and white colorings of the hex board, and you have functions on that, for example, the crossing function, the indicator function of having a left-right crossing. And so that L2 space has a very nice orthonormal basis with respect to this usual inner product, which is just the expectation of the products, which is just the product of the bits. So this is an orthonormal basis, and you can take the Fourier expansion in this basis, which is just this. It's called the Fourier-Walsh expansion. And you can do a little bit strange thing. This is like a bit like what quantum mechanics does, that you can encode all this information about the Fourier coefficients into a random set. So by Parseval, the sum of the Fourier coefficients squared is just the L2 norm of the function squared. Okay, so if I normalize by this, I can just define a random set, a random subset of the bits corresponding to f. So the probability that the spectral sample is this given S is just the normalized Fourier coefficient squared. So this way I get a random subset of the vertices. So I get it in one piece. It tells me the distribution. So how is this useful? For noise sensitivity, so Christophe showed you this formula that if you have a configuration omega and you resample each bit with probability epsilon independently, so this is the noised version of the configuration, and you look at the correlation between and after the noise, then you can write this very nicely in terms of the Fourier coefficients. So you have the sum over non-empty sets because I subtracted this thing here, which was exactly corresponding to the 0, to the empty set. Okay, so if you do this little L2 arithmetic, you get that you get this formula. So the correlation is basically somehow is measured by the size of the typical size of the spectral sample. So typically in what sense? You can see from here that so you are taking a noise epsilon. If there is no weight between 0 and some large constant over epsilon, so the probability of those samples is very small, then that part of this expectation will be small. And for larger sizes, it will be small because it's an exponential thing. So this whole thing will be small if you don't have mass between 0 and k over epsilon. So which means that if you want to show that epsilon noise already made you decorrelate, then you want to show that there is no with this strange random set doesn't have, it's unlikely that it's non-empty, but it has this size. So we are after such lower tail bounds for noise sensitivity. And so at least to us, it was Gil Kalai who suggested that although we are really interested only in the size, there was no, right? I mean, here it's only the size of the set. To understand that size, maybe we could look at the whole distribution as a random set for critical percolation, say for the crossing in an n by n square. It's a random subset of the n by n square. So we should look at it as a random set. And so it's a strange set, as I said. We don't know a way to sample from this set, for example, effectively. There's some relation to quantum world is that there's a theorem due to Bernstein and Vazirani that if the Boolean function itself is polynomial time computable, then there's a quantum algorithm to sample from this spectral sample. Okay, I don't know. Maybe there are some conjectures that say that it shouldn't be possible. I have no idea if it's possible to sample or not. I mean, I don't expect anything. I don't know anything about quantum algorithms and stuff. Okay, one sign that looking at the spectral sample for critical percolation could be interesting is that Boris Cyrelson has a theory of noises, and this combined with there's a Schramm-Smirnov theorem saying that the scaling limit of critical percolation is a noise. I don't tell you what that is, but so Cyrelson's theory of noises does apply, and from that and Smirnov theorem that critical percolation has a conformally invariant scaling limit. The combination of these things says that the spectral sample, so the left-right crossing in a conformal rectangle, so just take a domain with 4 marked points, and I'm interested in the left-right crossing in this conformal rectangle with mesh 1 over n. So this sequence of random sets as n goes to infinity has a scaling limit, and the scaling limit is conformally invariant. It doesn't say quantitative anything about the scaling limit, but certainly it should be some sort of interesting object. Now, also, maybe this came up in the previous talks, at least so it has something, the spectral sample has something to do with pivotals. So if f is plus minus 1 valued, then you can talk about pivotal bits. So those are the bits that if you flip the bit, then the outcome of the event changes from plus to minus 1 or vice versa. So it's not hard to see that the probability that a site is pivotal is exactly the probability that the site is contained in the strange spectral sample. And this is also true for pairs of points. Okay, but it's not true for more than pairs. So for three tuples, it's not true anymore. So this is also Gil Kalai's observation, which sort of says that it does have a lot. This set does have a lot to do with the set of pivotals, but it is different. So both random subsets measure the influence or relevance of bits in some sense, but in a little bit different senses. Okay, at least for left-right crossing in a quad, you can show that the probability that the spectral sample intersects some simply connected subdomain B is comparable to so up to constants is the same as the probability that subdomain B is pivotal for the left-right crossing. So a subdomain is pivotal means that if you change all the bits to all black inside the domain or all white in the domain, this makes a difference. And that is basically the probability that you have the 4-arm event from the boundary of B to the boundary of Q. So what is this 4-arm event? So like a bit is pivotal if and only if it's very easy to see that you must have so if you are interested in a white left-right crossing, either you have a white left-right crossing or you have a black top-down crossing, exactly one of these two. And a bit is pivotal if you have a black arm connecting it to the bottom, a black arm connecting to the top, a white arm connecting to the right, a white arm connecting to the left. So if it's white, then you do have this, and if it's black, you do have that. So this is the forearm event. So this forearm event is something that is understood well for critical percolation due to SLE. Okay, and okay, there's another small fact that, for example, the probability that the spectral sample is contained in some, say, box B, but is non-empty, is the square of the forearm probability. So this is very special to percolation. So for other Boolean functions, you won't get something like that. And also, for example, so this is already one sign that for pivotal something is different than for the spectral sample, is that the probability that all the pivotals in the configuration is inside this box B, and you do have pivotals, is not the square of the 4-arm probability, but is the 6-arm probability, which is different from this. Okay, so what do I want to say? Okay, so we have this spectral sample just to, I mean, you have sort of seen these examples in the previous two talks. So for example, for the dictator, which is just, say, the first bit, it's very noise stable because you have to touch the dictator in order to make a change. And there the spectral sample is concentrated on the dictator, with probability 1 is the dictator. Majority is still noise stable. The spectral sample, most of the mass of the spectral sample is concentrated on singletons. Now, of course, distributed evenly on all the singletons. However, there is some interesting thing is that, so since the probability of being pivotal and being in the spectral sample is the same, the expectation of the two sets are the same. And the probability that a bit is pivotal for majority, so with probability 1 over square root of n, you will have the same number of plus ones and the minus ones. And once you have this situation, every single bit is a pivotal. So with this small probability 1 over square root of n, you will have n pivotals, which means that the expectation of the pivotals will be large. It's huge. It's square root of n. So the expectation of this spectral sample is square root of n. On the other hand, most of the mass is on singletons. So this shows that it's not at all the case that the spectral sample is always constant, kind of typically the size of its expectation. There are examples where it's not at all true. Okay, last simple example is that parity. You just multiply the bits, and that's the most sensitive to noise function that you can imagine. The spectral sample is concentrated on the entire set. Whatever you change everything. Okay, now the spectral sample for the left-right crossing in a, say, n by n square has some, basically following from the conformal invariance of, or not, well, maybe the existence of the scaling limit of critical percolation. It has some very nice self-similarity properties. So just on the level of expectations to start with. So the expected size is, so it's n squared, the number of bits in an n by n box, times the 4-arm probability from distance 1 to distance n. That is known to be n to the minus 5 quarters from Smirnov-Werner. So you get some power, n to the 3 quarters is the expected number of, the expected size of the spectral sample. Now, if you look at this on a coarser scale, so you take a super lattice of medium-sized boxes, so R by R boxes, and you look at this super lattice, and look at which R by R boxes are intersected by the spectral sample. Now, by this previous result that I was showing you, so the number of boxes is n squared over r squared, and the probability that the spectral sample intersects an r by r box is the 4-arm probability from distance little r to n. It turns out that, so this expected number is exactly as if you were looking at the spectral sample in an n over r by n over r box. So somehow when you look at it on the large scale, it looks like the same function on that supergrid. Okay, and so this is one form of self-similarity. And another form of self-similarity is that if you condition on the spectral sample intersect into some R by R box, then inside the R by R box, it will look somehow like just if you had taken the crossing in an R by R box. So at least for the expectations, the expected size there is the expected size of SR, so the left-right in an R by R square. Of course, these two results are compatible with each other in the sense that also in the proof of these, you use the quasi-multiplicativity of the alpha for sort of the 4-arm probabilities. What does that mean? So if you look at this, so if you multiply the number of R boxes, the expected number of R boxes intersected times the expected size of the intersection once you intersect it, this product, of course, should give the expected size of the entire set. And it does give. So this is the compatibility I told you. So the point is that in order to have, so the probability that you have the 4-arm event from distance 1 to n is up to constants is the same as having it from 1 to r and then having from r to n. So of course one is bigger than the other because if you have from 1 to n, then you also have from 1 to r and you have from r to n, but also the other way. So once you have from 1 to r and you have from r to n, with positive probability you get the connection, you get the 4 arms from 1 to n. So this is a nice property of critical percolation. So all these formulas would be true for the pivotals as well. There is nothing special to the spectral sample. The pivotals are also like that. A more classical example is if you take the zero set of one-dimensional simple random walk or one-dimensional Brownian motion, so of length n, then the size of the zero set is around square root of n. Now if you take R boxes on the line, so R intervals, then, so for example, in the second thing is that if you condition on that you have zeros in this specific R interval, then of course the expected size there is around square root of R, which is about the size of the number of zeros in a length R simple random walk. And maybe from this or from other considerations, you also get that the number of R boxes that you intersect is typically the size of the number of zeros for a simple random walk of length n over R. So you do get this self-similarity in many instances of probability. Yes, and maybe this self-similarity can be looked at as somehow somehow it's a result of having a scaling limit for these sets. Okay, now, so you have this self-similarity. What type of concentration do you expect? So Christophe explained that the intuition is, or the hope was for a long while, that the spectral sample should be concentrated near its expectation. So why do you expect that, and what kind of concentration do we expect? Okay, so these are just silly examples. If you know probability, it's obvious. So say if you take a uniform set, so just IID set with the same density, well, surprise, surprise, it will be more uniform than a spectral sample. So it will intersect more boxes, but the intersection within a given box will be smaller. So it doesn't have the clustering effect that the spectral sample does. And there you get just CLT, what's it, central limit theorem, that the concentration of size, so really most of the mass is within square root of the expectation. Okay, a bit more similar to the spectral sample is where you take, so I fix some R, which is some medium box n to the gamma, so gamma between 0 and 1, and I take the supergrid and I say, well, let's take a IID sequence again, but now the probability, so with some small probability, which is the probability that the spectral sample will intersect that box, I take a large x, which is exactly the expected size of the spectral sample given that it intersects the box, and otherwise it's 0, so it is more similar. And then I take the sum of these independent things. Now this is still, you can also, some generalization of central limit theorem tells you what concentration you get. It is a bit more spread out than this completely uniform thing. but it is still little O of the expectation. Now, if you have this self-similarity stuff going on every level that you can imagine, then you don't expect this little O anymore. So somehow you get the same phenomenon on every level, and you get that you expect only tightness around the mean. So you expect that the probability that the spectral sample is non-empty, but has size smaller than lambda times its expectation should go to 0 as lambda goes to 0. And we did get, so we would like to get the exact rate depending on lambda, and we did get the exact rate depending on lambda. So how can you get such a thing? Okay. So if you had a lot of independence, then how would the proof of the tightness work? So for example, for the 0 set of one-dimensional simple random walk, you can do that. You can run the proof, the following proof. So what is the probability that, so conditioned on the event that the 0 set intersects an R box, and conditioned on everything else. So the set of zeros in all other R boxes on the interval. So with all this conditioning, still for zeros, it's obvious that the probability that you have at least constant times the expected number of their expectation you have some positive probability for that. So this is just the second moment method, Cauchy-Schwarz, or what is it, Paley-Zygmunt, or something like that. Okay, so this is easy for the zeros. And another one, so this is somehow, so what is the probability that you intersect only very few R boxes? It should be very close to the probability that you intersect only one R box. So you need this sub-exponential in K correction. This is the statement. So this statement is it's a result of the clustering effect that I was telling you. So if you have these K R intervals, if you think that they are pretty far from each other, then the probability, you have to pay K times the probability to get to the set and leave the set. And this probability is too big. So it doesn't discuss, it's not balanced by, so you have more ways. If the case R boxes are far from each other, then you have a lot of combinatorial ways to play with them. But this combinatorial entropy is not balanced by it doesn't balance the cost that it takes. So you can, with a little bit of work, you can prove this for the zeros. Okay, and once you have these two properties, how the proof looks like. So the probability, you take some whatever R, your favorite R. What is the probability that the 0 set is at most C times this expectation? Well, you break it into the events that the number of R boxes intersected is K. Now, given that you have, so condition on having K R boxes intersected, for each of them, independently of all the others, this is this conditioning there, you have probability C to have already a lot of points in there. So the probability that you failed all the time is at most 1 minus C to the K. And so you have this line, and from this by 2, so this thing grows sub-exponentially in K, and this thing decays exponentially in K. So you get is basically this probability that you have only one up to constant factors is the probability that you have only one intersection. And that you know for simple random walk, it's well, the number of these boxes is n over r, and the probability that you get there and leave and don't come back is n over r to the minus 3 over 2. And of course, the opposite direction is obvious. So once you just condition to have exactly one box to intersect, then this is the number of intersections that you expect. So, and then you take lambda to be the ratio between C times this E of expectation of ZR and the expectation of Zn, the expectation of the set that you're looking at. So if you take this lambda and you plug this in, you get for simple random walk, the probability that the zeros is less than lambda times expectation is roughly lambda. Okay, I have 3 minutes. So the problem is that we don't have that much we have no idea if this amount of independence is true for the spectral sample or not. We have only this very limited independence. So if you condition on the spectral sample to intersect a ball, an R box, an R by R box, but you condition on, you cannot condition on anything. You must condition on some W is not intersected. So this W set could be anything, not very close to the ball. But all the conditioning that we can handle is a completely negative conditioning. You must condition that it doesn't intersect W. And under this conditioning, we can prove this conditional second moment and hence this positive probability result. So where does this negative conditioning comes from? Why it's only negative conditioning? So the probability that we can handle this probability, the probability that the spectral sample is contained entirely in some set U, some subset of the bits. So that's just taking all the Fourier coefficients corresponding to inside that U. And this is like a projection. So it's not very surprising that it's exactly like a projection of taking a conditional expectation. So this is this conditional variance. You can easily check that. Which means that, for example, for two disjoint sets A and B, the probability that the spectral sample intersects B but doesn't intersect A, you can interpret it as probability of contained in something minus probability of not contained, of contained in something else. So this is this thing, and then you use the Pythagoras theorem for martingales, or something like that. So you get, the point is that the whole strategy for the spectral sample of Fourier spectral sample of critical percolation depends on the fact that this sort of inclusion formula and this sort of probabilities we can understand in physical space. So because these conditional probabilities and the conditional expectations can be rephrased in terms of four-arm events here and four-arm events there, very briefly. So whenever you have a Boolean function for which you can understand in physical space this sort of probabilities, then you have a chance to run our strategy. And okay, and now here comes so we have these two results. So actually, so I didn't say how to prove them. So one is we have this replacement when you already have this negative conditioning, and you also have some clustering effect, similar to the zeros of the Brownian motion. So alone, each of them was a lot of work to prove. But assuming that you have these two, what do you do? Well, the trouble is that you cannot repeat that calculation that I showed you here, because I cannot just take the case power that I would like, because I need whenever I failed to have a large enough intersection, I cannot just just go on because I don't have the independence. I could go on if not enough points, so a failure, not enough points in one box, if it meant we found nothing in that box, then we sort of could go on. Okay, so there is a simple remedy for that. This is a nice idea. You take an independent random dilute sample. So you take a random subset independently of everything with the right size such that if an R box, if the size of the sample in an R box is small, then it's likely that it didn't intersect the dilute sample. And if the size is large, then it is likely that it intersected. Which means that you can measure if it's small or big just by looking at whether it's empty or not. So failure will be empty. So you have only negative information that you gained by looking at this dilute sample. So now you have a chance to do. However, there was another problem, which is that you had also this conditioning that the number of, when you want to put 1 and 2 together, you wanted to use that the probability that the number of R boxes intersected, the probability that it was small. And this conditioning is not a negative conditioning. So we cannot just take the case power of this 1 minus c, because there is this positive conditioning. And what do you do with that positive conditioning? And okay, we were completely, it looks like a silly technical problem, really. And while we were with Christophe, we were digesting how silly this problem is. So Oded first came up with one solution, and Then while we were digesting that solution, he came up with another solution. So the first solution, so you can try to do something like you scan sequentially the boxes with this random dilute sample. And so if you see that you didn't succeed, you didn't find anything, it's empty, 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 you go on. And so if you could say somehow that with good probability you had many chances you had to find something, then you would be fine. So the question is, how do you put this thing in that actually we had a large number of boxes intersected? So the first solution was a filtered Markov inequality, which is that, so if you have some non-negative variables, so it's extremely general, some xk non-negative variables, and some fk is a monotone increasing filtration. So this is somehow what you learn during this scanning process. And the yks are the conditional expectation. So the probability that the unconditional ones is large and the conditioned ones are small is small. So you can try, so there's a very simple proof due to Asaf Naor. You can try to this homework. So this sort of gave some solution to our troubles. The problem is that this is just a Markov inequality. It's too weak. We didn't get the full result that we wanted. So Oded came up with a better solution, where I will end. Almost. Okay, so sorry. Yes, yeah, okay. So this is a strange large deviation lemma with very dependent things. So this is exactly the type. So instead of scanning sequentially, we know that if we have an information about any set of boxes that we didn't intersect there, given that the spectral sample is there, we have a positive probability that there is a lot of intersections, so the random dilute sample will find that. So we have this type of thing. So in order to get an exponential large deviation thing, instead of doing this sequential scanning, you average these inequalities at once. So you take a suitably chosen random j, and take the expectation of this inequality, and you get something, and you get this. So Oded, well, we asked, how did you come up with this proof and this result? And said he tried not to think probabilistically, but rather, well, we have a bunch of inequalities. We wanted to get another inequality. He tried to be an analyst and do something. Okay, so this is what's solved, and then, so with this we actually get the final result that we get is that the probability that the spectral sample is less than the expected is something is basically equivalent to contained in a single R by R subsquare, and that we know. I showed you on the second slide, and so we do get some result, and we get that the scaling limit of the spectral sample is conformal invariant Cantor set with Hausdorff dimension 3/4. And you could run the same process with pivotals, but you get some different exponent here. But it's an overkill to do this, because pivotals have much more independence. So you don't really want to do that. And I stop here. Thanks.
Comments or questions?
So if I understand, so one of the worries is that this thing is not independent, this set. So can you prove anything that it's not independent? So do you expect clustering, I guess? Is that
Yes.
the idea? So can you prove that it's more clustered than...
Well, there is something about... so pivotals has a lot of independence. So there you can say that however the set of pivotals looks here, if you condition to see pivotals in here, then the configuration inside here will be basically independent of all the other conditionings that you made. So for pivotals, we know that. So pivotal still has the clustering effect. It has the same type of clustering as the spectral sample, but it has this independence, this approximate independence thing. And we don't have a clue about the spectral sample. So actually, there is one thing that I wanted to mention, that Gilkalai has a conjecture that the entropy of such self-similar sets should be just bounded by the expectation of the size of the set, so the log factor shouldn't be there that you would get from uniform. So that, for example, I think I can prove for pivotals, but not for the spectral sample.